Hi everyone, this is the vector review section. I'm going to be solving one of the examples just to make sure we are on the same page when it comes to the notation. Your previous teacher might have been using a different notation with respect to vector compared to my notation. So let's solve one example and just make sure we are clear for the remaining of the semester. So I'm going to be solving question A from the vector section chapter. So let's read the question first. Question A. Find the resultant vector in polar coordinate from the addition of vector P and F. If the magnitude of vector P and F are 35 meter and 50 meter respectively, we have a diagram with this question, and the diagram looks like this. We have an XY axis and we have vector P and vector F. Vector P has an angle of 20 degrees to the left of the positive Y axis. Vector F has an angle of 40 degrees to the right of the negative y-axis. We are also given the magnitude of both vectors. Vector P is 35 meter. Vector F is 50 meter. Now, when dealing with vector, or in this case, a vector addition, what we want to do is we want to take each vector and break them down into their 1D x and y component. After doing that, it will enable us to add the x and y component together and then reform the vector in polar coordinate. So graphically, what that means is, let's say we have our vector P over here. We want to create two vector Py. So let's look at vector P. It's pointing the positive y direction. Therefore, Py will be pointing the positive y direction. Px would be pointing in the negative x direction. Now, by the way, it's really important to pay attention to which direction are these vectors pointing. Are they pointing in the positive direction or in the negative direction? When dealing with 1D vector, the plus or minus sign in front tell us the direction. A 1D vector can only go in the positive or in the negative direction. So it's really important to pay attention to that sign. In this case, Py will be positive, Px will be negative. We follow a similar logic for the vector F. So vector F is going in the negative y direction, so Fy, and we got Fx here. Now note, if we were to draw a vector linking the origin to the tip of the last vector, we will get back to our vector F, and same logic for our vector P. Now, in order to break down these vectors into their x and y component, we need to use trigonometry. So if we look at this vector over here, or actually it might be easier to see it on these one over here, these two vectors form a right angle, and therefore if we were to link with a straight line from the origin to the tip of the Px vector in this case, we will form a right triangle. And basically, the angle of our P vector over here, Px is opposite to the angle given in this case, it's 20 degrees. So if we want to find Px, we need to use the sine function. The sine is the ratio of the opposite side with respect to the hypotenuse. Now, as I mentioned previously, Px is pointing in the negative direction. So our vector Px is equal to minus, and this minus, to determine if it's a plus or minus here, really there's only one way, at least with this method. It's to look at where is the x vector pointing. In this case, it's pointing in the negative direction. If it were pointing in the positive, it will be positive, but now it's pointing in the negative direction. So we add a minus here. Since it's this, the side opposite to the angle, we use sine 20. We compute this value. Now note P over here is the magnitude, 35 meter. And we get a value for Px of minus 11.97. All right. Now we need to find the y component of our P vector. The y component is adjacent to the angle. Adjacent to the angle, which means we will need to use cosine. And Py is pointing the positive y. Therefore, there's a plus here. Now note, I will rarely write the plus in front. If there's no minus, it just means it's going in the positive direction. So plus P cosine 20 is equal to 32 0.9. We use the same logic for the f vector. So let's start with the fx. So fx is pointing in the positive x direction, which means it's positive. Oh, I actually made a mistake over here. This is not p, this is f. All right, so fx is equal to plus f multiplied by sine 40. Now again, sine, because the x component is opposite to the angle. So f multiplied by sine 40, we get 32.14. The y component now, you notice that the y component is pointing in the negative direction. That means we need to add a minus over here. Fy is equal to minus f cosine in this case, because the y component is adjacent to the angle, cosine of 40, and we get minus 38.3. All right? At this point, we took our two vectors and we broke them down into the xy component. What we need to do is take the x component, add them up together. Take the y component, add them up together, and then we are in a position to recreate back the polar coordinate of our resultant vector. So let's start by finding the x and y component of our resultant vector. So Rx, so by the way, the addition of these two vectors, I'm gonna use the letter R to denote the resultant vector. So in this case, Rx is equal to Px plus Fx. Now note, I have this arrow over here. Now this arrow state that it is the vector. Now to fully describe the vector, you need the magnitude and the direction. Since we are talking about 1D vector, the direction is a plus or minus sign in front. So when you add Px, you really need to add the minus over here. So Px plus Fx, so we got minus 11.97 plus 32.14, and we get 20.17. Same logic with Ry. It is equal to Py plus Fy, and we get minus 5.4. Again, for the Fy, there's the minus here. We absolutely need to include it into this calculation. All right. Now, in order to solve the remaining of the problem, I will be erasing the top part, because when I get to the resultant vector, I love drawing on an xy axis what my vector is supposed to look like. It makes it easier to determine with respect to which axis the angle is. So if you need to pause the video and write these values down, do it now. All right, so just to get an idea of how our resultant vector is supposed to look like, let's draw the x and y component. So the x component is equal to 20.17, and our y component is equal to minus 5.4. So this one is supposed to be smaller than Rx. So let's draw a big vector Rx. This is our Rx. It is equal to 20.17. Then let's draw our Ry. This one is much smaller. It is equal to 5.4. Now note, I'm not writing the minus here. You will see why in an instant. And our resultant vector, the one we are looking for, the R vector over here, is here. And we are looking for this angle over here. Now, with your previous teacher, and that's the reason why I removed the minus over here, with your previous teacher, you might have written all the angle with respect to the positive x. So you would write from here to here. Now, it's fine with one vector, but when you're starting to add many vectors, it starts to be very cumbersome. So that's the reason why I like to interchange a sine or cosine and recreate a brand new triangle at each vector. I think it is a much easier way, a much more intuitive way to solve these type of problems. So I'm not gonna get this angle. I'm looking for that one over here. Now, one of the problem by not having a convention, in other words, not always picking the angle from the positive x, is that we need to specify with respect to which axis we are taking our angle or calculating our angle. So this is a right triangle. This side is a right angle over here. So we can find the magnitude of our resultant vector by using the Pythagorean theorem. So it's Rx, well, the two sides of the triangle, square. So Rx squared plus Ry squared, square root the answer, and we get 20.9. And this is in meter, by the way. All right. Now, before I explain the angle over here, let's just have a look. We are given the two sides of the triangle. At the beginning, we don't know the magnitude. We don't know the angle. If we want to find the relationship with these two sides, we need to use the tangent. So tangent of theta, in this case, is equal to Ry divided by Rx. This is another reason why I'm using the positive value here. If you were to use the negative value, in this situation, it will be fine. It will tell you that the angle is minus 15 below the x-axis. But if you were to have an angle over here, you will still have a minus, and a minus. The minus will cancel out, and the tangent will kind of tell you that the angle is on that side, which is not the case. Okay, we will be solving some example later on where this is the case. So here we know that the tangent of theta is equal to the opposite side divided by the adjacent side. And if we isolate the angle, so this is the logic, this is the computation over here. So theta is equal to the inverse function of tan, so we cancel out the tan here to extract the angle. I added the absolute value, I want to take the positive value, and I get 15. And if you notice here, it is 15 degrees below the positive x-axis. All right, you could also write it is 345 degrees, so this one is 15 degrees, or you could write it that way, 355 above the positive x direction. Now, because the reference point will change from problem to problem, you should probably simply write down 15 below the positive x-axis. All right, so that's it for the vector section. In the next video, we are going to be solving some problem with respect to the Coulomb force and the electric charge. All right, so see you in the next video.